Welcome back everyone to your favorite math channel, VHS Math. Today we're going to learn integration. The question that we need to understand is, how does the integral represent the summation of an infinite set? To understand that, we first need to understand why we even use integrals in the first place. Let's look at the first problem on the worksheet. We are given a table of speeds for a car over 12 seconds. The speed starts at 30 feet per second and increases to 65 feet per second. The car is speeding up the entire time. We are asked to estimate the total distance traveled. If the speed were constant, this would be simple. We would just use the formula distance is equal to speed times time. But the speed is not constant. It is changing every second. There's no single number we can multiply by 12 seconds to get the distance. That's the main issue. When a quantity is changing continuously, we cannot use a simple multiplication formula anymore. We need to use a new method. The method is built for Riemann sums. Why we use Riemann sums? When we can't calculate exactly, we have to approximate by drawing a line and breaking it down into smaller pieces. In this problem, we break the 12 seconds into smaller intervals. On each interval, we pretend the speed is constant. This allows us to use a formula where we use distance times speed. The distance is equal to speed times height. Each small rectangle represents width, the small time intervals, height, which is the speed during the intervals, and area is the distance traveled during the small piece of time. When you add up all the areas of the rectangles together, we're adding up small pieces of distance. So, let's see how it works. So the line looks around like that. And then, we are going to create little rectangles inside. And to find the sum of all these rectangles, we call it a Riemann sum. They allow us to approximate the total accumulation when a rate is changing. They turn a continuously changing situation into many small, constant situations that we know how to handle. So, what is the three different Riemann sums we're going to look at are left, right, and midpoint. For a left Riemann sum, we use a speed at the beginning of each interval. Since the car is speeding up, the speed at the beginning of each interval is smaller than speeds later in the intervals. That means the rectangles sit below the curve. So the left Riemann sum gives an underestimate. Let's see how it works in this equation. So, our base is 3, since we use b times h for the rectangles. Then, we can add up the numbers in the table. So we get 30 plus 37 plus 45 plus 54. Sorry for the messy handwriting, but this is equal to 498 feet. Okay. Now that we understand that the left Riemann sum is an underestimate, the right Riemann sum will then be a overestimate. So let's graph it out. So, since it's an overestimate, we're going to have bigger squares, rectangles. So, that's how it looks like on a graph. For the right Riemann sum, we use a speed at the end of each interval. Because the speed is increasing, those values are getting larger. The rectangles sit above the curve, so the right Riemann sum gives you an overestimate. So, let's do it for question C. Okay, so we are going to start from the right side. Since our base never changed, which is 3, we're going to put 3. Then we're going to multiply it by the right side towards the left side. So 65 plus 54 plus 45 plus 37. And this gives us 603 feet. Perfect. See? The left Riemann sum was smaller than the right Riemann sum. So, we understand that it was an overestimate. Now, let's look at the midpoint Riemann sum. This uses the values in the middle of each interval. It often gives you a better estimate because it balances being too low and being too high. Let's draw the graph again. So, same graph, like this, around like that, something like that. Then, we're going to separate it into 2 pieces. There we go. The graph is in two pieces. Separated in 2 pieces. Okay. Then I will color the boxes. One here and one here. To find the midpoint Riemann sum, we have to use approximation. So our base here, since it's 2, we have to divide the box into 2 sets. So 12 divided by 2 is 6. So now our base for each one is 6. Then we take the middle value between 0 and 6 and 6 to 12, which is 37. And then same thing, 6 times the middle value between 6 seconds and 12 seconds is 9 seconds, which yields 54 feet. And this goes to 546 feet. Good, we figured it out. So, how does a Riemann sum have to do with integrals? A Riemann sum uses finite numbers of rectangles, but what is the use for more rectangles? What if we made them thinner? As the rectangles get thinner and thinner, the approximation gets better and better. If you imagine using infinitely more rectangles, each infinitely thin, the approximation becomes exact. That exact value is called the integral. So an integral is not something completely new or mysterious. It's the limit of Riemann sums. It presents adding up infinitely many pieces. That's why the essential question says an integral represents the summation of an infinite set. It's literally the sum of infinitely many tiny rectangles. So why does this matter? We use integrals whenever you want to find the total accumulation and the rate is changing. In the worksheet, we saw the 3 examples: the total distance when the speed changes, total area under a function, and how that works. The graph represents the rate of a function, and the area in the graph represents the total accumulated amount. So thank you very much for listening to my video. If you want to see more content, comment down below. We'll get you more like this.